Yeah, Steve Jones from Huber+Suhner. For those who, thanks very much to the committees and everyone organising all of this. Thanks to Anne for helping solidify my thoughts, because the first version was a bit more all over the place. So Huber+Suhner, we're a Swiss-German organisation, as you can tell from the accent. I'm not Swiss or German, but we do all sorts of stuff from muxes to PON splitters to cables to amplifiers to or anything layer 1. So we're going to talk about layer 1, really exciting stuff. So what is WDM? What is wave division multiplexing? If you want to connect from site A to site B, it's quite simple. You put a transceiver in one end and you put a transceiver in the other end, and voila, my best French, you have a service. Simples, as the saying goes. And if you want a second service, you plug a second pair of transceivers over your fiber cable, and away you go. These transceivers are typically 1310, 1550 grey transceivers, but you want a third one, you've got a third fiber, carry on. You want a fourth one, got a fourth fiber, carry on. It's all really simple stuff. And it's great if you've got lots of fiber. Great if you have lots of fiber. But what if you don't have enough fiber capacity? You could install more fiber. Good luck with that. You could dig up the roads, try and get wayleave, try and stop everything. It's always interesting when there's rivers in the way. That's going to cost you not only a lot of time, but also a lot of money. You could rent more fiber. There are dark fiber providers in the UK and every other country who would be happy to rent you more fiber. And there's some salespeople, I'm sure, would be more than happy to rent you more fiber. Or about if you just combine over one fiber. So if you have one color, so we're now going into colored optics. They might heard them called color optics. And in this instance, we got a green one. And if you want a second service, you add a red one. You add a third one, which is blue, and a fourth one, which is a dark blue stroke black, because I can't see properly from this distance. So you put them over a mux and a demux. When we talk about muxes, we're often inferring demux as well. So when I talk about multiplexing, I'm often inferring demux as well. And so long as you match the lambdas, the colors at each end, away you go. You can just add as many services over that fiber pair or single fiber working as you wish. And that, effectively, is WDM. Oh, sorry, right. But we don't want to keep things simple. Unfortunately, there's different types of WDM. There's coarse wave division multiplexing, which is 20 nanometers, all defined in ITU-G 694.2, or if we're talking about DWDM, it's G709. There are other WDM blocks available in the L band for long-haul submarine stuff, but I'm not going to touch on them. I'm just going to use the two most often used within the telecoms industry, which is CWDM and DWDM. You can mix DWDM and CWDM. The only thing you cannot do, which I'll come back to a couple of times, is you cannot send the same frequency, the same lambda, over the same fiber. But other than that, you can mix and match as you want. Every single vendor uses exactly the same lambdas as specified by the ITU. So vendor A and vendor B will always use the same lambdas. Channel 21 within the DWDM spectrum is the same across all vendors, as is channel 22, 23, 24, etc. What about PON? Because I know there's a lot of people who are building PON networks. Again, so long as you're not... there's different types of PON. I should explain that. So there's certainly different types of PON within the network, and depends on which version of PON. But again, provided you're not using the lambdas as specified within the type of PON you're using, you can send PON and WDM over the same fiber. Another interesting thing, interesting, is OTDR. The OTDR port, if you notice right on the right-hand side in the purple, the 1625, it's normally 1625 or 1640. So you can easily add an OTDR port to any mux, so you can do remote management diagnostics, so you can work out over time what's going on over your fiber network. You can run monitor ports over these networks as well if you want. So you can, again, so long as you're not using the same lambda more than once, you can mix and match all these things as you wish. So types of muxes. When we talk about WDM, the majority of people automatically assume it's a fiber pair, and that's fine. So in this instance, we're showing 8 colors coming in over a common port going out, and then in the other direction over a fiber pair, the common port coming in being split out into 8 separate lambdas. That's WDM. That's what it does. It's a filter that separates the light into different frequencies. You can do exactly the same over single fiber working. The positive of that, of course, is you're only renting one fiber rather than a fiber pair, which is cheaper, and also lower fiber tax in the UK. So single fiber working is much lower fiber tax in the UK. The downside is you halve the number of available channels. So if you want 8 services from point A to point B, you would need a 16-channel single fiber working mux to enable you to do that. But you could still use standard, exactly the same transceivers over dual fiber or single fiber. You don't need special transceivers for running over single fiber working. You also have these things called optical add-drop muxes, where you're adding and dropping one or more lambdas at a midpoint. So you have 2 common ports, and then it's up to you whether you want to drop 1 lambda, 2 lambdas, 4 lambdas at a midpoint, and then also add 2, 4, whatever number of lambdas at that midpoint. You can also do single fiber OADM. Exactly the same, provided you're not sending and receiving the same frequency, the same lambda. You can add and drop over single fiber working just like you can over dual fiber working. The downside, again, is you reduce the number of available lambdas by 50% because you can't send and receive that same lambda over the same fiber. But other than that, you can mix and match these things as you desire. So this is an example in the US. This is a neutral host. They're providing connectivity to a number of mobile operators in the US. And they've got a 40 to 80 kilometer reach using passive muxes, adding and dropping 8 lambdas at these intermediate points. Really cost-effective way of delivering WDM if you're renting a fiber. You'll notice on the left and right-hand side, there's amplification added as well because of the reach. We also add amplification at either end just to extend the reach of the service. There's also monitoring. So these are actually enclosed in splice cassettes. So they're in CommScope, I think, splice cassettes. So we can put this stuff in really outdoor, harsh environments in splice cassettes where space is a limitation. Really cost-effective way of delivering connectivity within a mobile environment for that X haul, be that front haul or back haul. I want to talk about passive and active WDM now. The majority of people, when they think about WDM, automatically assume you have things called transponders. And what a transponder does, it takes a grey optic in, it'll transpond it to a colour and send it out over the WDM mux. The mux itself, however, is passive. It's a filter. Bidirectional, but it's a filter. The downside of using active systems is you require power, you require a management system, you require northbound interfaces via your whatever northbound management interface that you may require. The transponder is often linked to speed and type, so it's a 10 gig, 25 gig, 100 gig, 400 gig transponder. But if you have a remote site and you need diagnostics, you need to be able to do loopbacks and be able to monitor what's going on, you'll need an active system that has a clear demarcation between the client side and your side. So There's pluses and minuses. A passive system, however, is agnostic to the service type and the power that goes over a passive system. It's a filter. So it doesn't care if it's 1 gig, 10 gig, 25 gig, 400 gig. We were talking about 800 gig and terabit type transceivers that are coming down the line. It doesn't care. It's a filter. So once you buy it, as long as you don't break it, it'll work forever. There's no conversion, and they plug directly into the end equipment. So you have to really own the end equipment that the colored transceivers are plugged into. But as a result, you have lower latency, lower power. Nothing to go wrong, other than plugging a dirty fiber in, maybe. The transceivers will be managed by the end equipment, or you can add an OTDR or monitor port onto that passive mux if you want to do some remote diagnostics and remote monitoring. And there's typically around lies, damp lies, and statistics, 80% power savings versus an active system, because you don't need to power that transponder, the fans and everything else that's going on within your active system. So should you use an active or a passive? It depends. So this is an example, and thanks to Andy Sutton from BT, this is a slide I took from one of his presentations. On the left-hand side, we have the optical filter, which is in the central office. At the remote macro site, there's a filter, and just for simplicity, we've got 3 colors showing here, a red, an orange, and a green. And then he takes it through a transponder at the remote site. And the reason for that is there's a lot of legacy equipment at this macro site, and the engineering hours to swap that out just are humongous. But the message is there's nothing wrong with you putting an active system at one end and a passive system at the other. So long as they're using the same lambdas, they will work. So long as they're using the same lambdas, they will work. You can see in pink that there's an alarm because he's actually put a monitor port or an OTDR port added to that passive filter so we can do some OTDR reflections to see what's going on at the remote site. So what about these things called transponders and muxponders and amplification and all this sort of stuff? You may still require, they may still be required in a transport system, but they're not strictly WDM. A transponder takes one lambda in, converts it, and sends it out via another lambda. A muxponder will take a service in, a wavelength in, and mux it onto another one out. For an example that's becoming more and more prevalent is maybe 4 times 100 gig in and 400 gig out. Dispersion compensation, how long have you got? You may or may not require dispersion compensation. That's a talk for another day. Amplification, you may require amplification. You can amplify, typically amplifiers work around the 1550 nanometers, around the C band, but you can also you can amplify in the 1310. You can also do optical protection switching, which is quicker than a layer 2-3 reroute. The other thing to consider is, do you do vendor lock-in, i.e. buy everything from one vendor, or seeing a growing want to buy what's best from various vendors and do open line systems. So you can buy the mux from vendor A, the amplifier from vendor B, the OPS from vendor C, plug it all in together, and it'll work. It's up to you to decide whether you want everything from one vendor or an open line system. We don't lock anything. So we're open to all vendors. This is a network in sunny South Wales, where I'm from, not that anyone noticed, I'm sure. And they use, they're building their own PON networks around towns and cities that are underserved by OpenReach. This is Oggy. It's in the public domain. So they're building the PON networks in these various towns, digging the roads and everything else like that. But between the towns, they're renting from OpenReach, typically. But they're renting a single fiber from OpenReach. And they use 20 channel muxes east, 20 channel muxes west, 40 lambdas to connect 10 gig, or they're looking at 100 gig between various locations. In one location, there's a river that goes between England and Wales. So one of the locations is 80-odd kilometres, so they've had to do amplification on one of the links just because there's a river in the way, and the fibre, just because geographically it's close, there's bridges. And they're also now looking at dispersion compensation because of things to do with 100 gig. So you can mix and match all these things. That's the message. So in the last 5 minutes, I'm going to talk now about what about these higher data rates, 100 gig and 400 gig. It's all about your modulation. Ooh. Most 1 gig and 10 gig, and up to 25 gig, will use NRZ, non-return to zero, for modulation. And what we're looking at here is the optical eye. So your receiver has to see a good signal on the receive end to understand whether it's a 1 or a 0. That's basically what it's doing. If it can understand if it's a 1 or a 0, it can understand what's being sent to it, and everything works. Fantastic, really simple. As it says here, it's higher attenuation compared to PAM4. So PAM4 looks at 4 different states. The downside, the positive, it gives you double the sample, double the data rate. But the downside is it becomes really susceptible to dispersion compensation and attenuation. So if your receive end can't see that optical eye, can't work out whether it's a 1 or a 0, you'll start hitting bit error rates, and eventually the service will fail. With some of the newer coherent transceivers, we're now using QAM, typically 16 QAM, but 32 QAM and other modulation techniques are being used. It allows for far higher data rates than NRZ or PAM4, but requires much more complex modulation and demodulation. So anything up to about 25 gig will typically use NRZ. We're starting to see PAM4 around 100 gig, but the problem with PAM4, you can't typically shove it more than 10 kilometers. Shove it, that's a technical term. You can't send it more than 10 kilometers without having real problems with dispersion compensation, and you need to start amplification. 400 gig and 800 gig tend to use some form of QAM to give you that greater distance, which is why you can't get a 100 gig DWDM transceiver to push more than 10 kilometers today. So we look at the dispersion. The top green one is no dispersion, and then we see 87, 86 picoseconds per nanometer dispersion. You can see the optical eye disappears. There's no way that the receiver can actually understand what the hell's going on. With an NRZ at 25 gig, you can see there's still a decent optical eye. Just lead on this. I don't expect you to be able to read this at distance, okay? But what it's saying is attenuation around the C-band was chosen around 1550 nanometers because that was the lowest attenuation on the fiber at the time. The downside of that is dispersion works better around the 1310 nanometers rather than the 1550 nanometers. So we have this quandary of attenuation versus dispersion. What it means is a PAM4 100 gig really struggles, as I say, anything 10 kilometers and above. That is not going to change anytime soon. The 100 gig space is not, there's not much being done in terms of the transceivers at looking at how do you get DWDM greater than 10 kilometers. It's not happening because the 400 and 800 gig space are looking at QAM4, QAM 16 and QAM 32. And it's dispersion that's stopping that 100 gig stuff happening. There's more slides attached to this to go into this in a bit more detail if people want to look at this afterwards. So just in summary, Deploying WDM is quicker, cheaper, simpler than installing new fiber. No-brainer. An active system can make sense in certain circumstances where you need a demarcation device. A passive system makes sense in lots of other applications. It's a hell of a lot cheaper. Oh, by the way, did I mention we sell them? And it's agnostic to the data rate that runs over it as well. So do you want everything from one vendor, or do you want to start building open-line systems? And it's transceivers and transponders that determine not only the speed, but the distance, not the WDM mux. And finally, in case I didn't mention it earlier, all vendors use the same ITU WDM grids. Any questions?
So I have a question. Or James, do you know of anybody, nothing coming in remotely? Oh. So come to the mic.
There's people online, so they need to be able to hear you.
So sorry if this is a silly question. You spoke about the optical eye and had the graphs. I was wondering what that was showing in the X and the Y.
Oh, sorry. So basically, the X and the Y are showing basically it's a 1 or a 0. So on the receive end, is it able to distinguish whether it's sending a 1 or a 0? And the optical eye over time will narrow.
Yeah,
so
that was a time axis, and on the one which had the 16 dots, what was that showing? Was that showing was that time as well, or was that showing amplitude and phase or something?
That's actually in 2 phases. So basically, it's an X and Y axis that's sort of spread over, and I need to. So it's a much more complex modulation system.
But it sounded like it was using both the amplitude and the phase to distinguish the 16 dots.
Okay,
thanks.
Thank you very much. And one very brief question. Later on, John Baldry's talking to us about coherent pluggable optics. Can we assume that everything that you've described here basically gets contained into the pluggable optics once the standardization and process is complete?
When we're talking about pluggable optics, I assume we're talking about transceivers, whereas optics is a much broader term.
Okay. All right, we can hold it. I'll ask John the question too.
So, depends.
All right. So, thank you.
Any other questions? Okay. Thank you very much.